In this talk, I'll show you how to build machine learning enhanced streaming applications using Java. My name is David Kjerrumgaard, and I'm a developer advocate at StreamNative. I'm also a committer on the Apache Pulsar project and author of Pulsar in Action by Manning Press. I have extensive experience in software development, big data, and streaming in companies from Amazon to Zappos. So in this talk, we're going to start with discussing why Apache Pulsar is a great fit for event-driven microservices. Once we've covered that background, I'll show you the steps required to build an event-driven microservice using Pulsar functions, and finally, how to enhance your event-driven microservice to include machine learning algorithms. So what are event-driven microservices? In an event-driven architecture, you decompose a larger application into smaller individual units called microservices. These microservices communicate with one another by passing messages back and forth. Now, some microservice architectures prefer to use point-to-point communication using gRPC or other network-based protocols to make calls to one another in real time. Now, with an event-driven architecture, this interaction has been shifted to a message broker, or an intermediary that will store the messages and forward them on to other microservices interested in these events. Another architectural distinction between an event-driven architecture and other traditional architectures is the fact that everything is based on events. An event represents a change in state within the application itself, or something that has occurred within the system, such as an item being placed into a shopping cart, an order being placed, a shipment being fulfilled and dispatched, etc. So the event producers publish these messages to the message broker, and then various applications subscribe to the message broker and react to these events as they come in real time. Microservices within an event-driven architecture communicate over this event bus. This event bus serves as an intermediary between all the different applications within a system and guarantees that messages are delivered even in the event of a temporary outage between one application and another. So as we can see here, events coming in from a retail website will go through the message bus and get shipped to the warehouse who needs to fulfill them, to the finance department who needs to track and record this information, collect the data, collect the money, apply tax, etc. And then these events would be triggered out once the warehouse is fulfilled or shipment has been completed. Another event will be sent to track the delivery of these applications as well. So again, all this information is passed between these microservices on an event bus. In short, event-driven microservices need this event bus. It's a critical part of an event-driven architecture. So now let's talk about Apache Pulsar and why it is a perfect fit for this message bus within an event-driven architecture system. As most of you know, Apache Pulsar is a cloud-native messaging and event streaming platform. It originated in 2012 at Yahoo, and it was designed to provide, among many other things, a unified messaging and event streaming platform. This is one of the key differentiators between it and other competitors, that it supports both messaging and event streaming natively, which makes it a perfect use case or perfect application for the event-driven architecture. Specifically, the fact that Pulsar supports a pub-sub model, which is exactly what we saw is required in an event-driven architecture. Event producers on one side must be able to send messages asynchronously to register these events, these changes to the system, and the interested consuming applications can register and get these messages and events delivered to them to receive this data and interact with it. This can all be done asynchronously. The producer and consumers are completely separated, and Apache Pulsar serves as the message broker between the two. It's the event hub that we saw on the previous slide, where messages are exchanged between topics. So it's a perfect fit for this particular architecture, and it scales horizontally, as you already know, making it an ideal candidate for this use case. As we know, Pulsar instances are consisted of multiple clusters. These clusters further break down logically the data storage into tenants, namespaces, and topics. This allows you to scale out and have individual tenants and namespaces and topics, multiple topics for exchanging data between an event-driven architecture. As your application grows, you'll need to have additional topics. Pulsar is built for that. That's another key critical component of the Pulsar architecture that makes it ideal for an event-driven architecture. As a point of review, again, the physical architecture of Pulsar cluster is separated into three individual components. There's a stateless serving layer called Pulsar brokers that handle, again, the interaction between the clients. They're stateless, so no data is stored with them, and allows you to assign different topics to different brokers dynamically. There's a separate storage layer based on the Apache Bookkeeper project that stores information in a segment-based model versus a partition-based model. Lots of advantages to that. Guarantees that the data is distributed evenly across all the brokers within this particular bookies within the Bookkeeper layer, and it retains all the data. And then tying the two together is a metadata storage component, which is now pluggable and includes support for things like Oxia, Zookeeper, etcd, and RocksDB, just to name a few. So again, it's highly scalable at its core. Additionally, Pulsar also supports what's called Pulsar Functions, which is a lightweight compute framework built on top of Apache Pulsar. And this is implemented by the use of function workers into this architecture. So they sit alongside brokers and bookies in this particular architecture and can be used to host Pulsar functions. So what are Pulsar functions? They're really, as I mentioned before, a serverless computing framework that runs on top of Pulsar. You can think of them as a function as a service offering similar to other cloud providers, AWS Lambdas, for example, where you have a very simple programming API, a single method that gets triggered and executed whenever a new event occurs or message arrives. So again, this is a key differentiator that allows you to react in an event-based model, it's an event-driven architecture. When a message comes in that you're interested in, the code will get executed automatically. And by using the Pulsar Functions framework, you do not have to write the boilerplate code that you typically do for creating producers and consumers. Instead, you can just focus on the business logic itself. It allows you to run these individual units of code, and they can respond to the publication messages. So again, they can be developed very quickly, deployed, and changed out very quickly. So again, they fit the microservices architecture and use case very well, that they're can easily be updated and deployed independent of one another as well. From a programming model perspective, this is how they're implemented. So a Pulsar function can consume messages from one or more topics. You can either provide a single topic, a list of topics, or regex expression mapping to many topics. Whenever an event occurs on one of those input topics that the Pulsar function is registered, then the user supplied processing logic that you encapsulated within your Pulsar function is executed. As an option, you can publish the result of this execution of your processing logic to an output topic in order to chain them together. So in this case, again, these dashed lines indicate an optional component, but you can obviously publish these results down to other topics. You can also configure it to have a log output topic, so you can track and monitor the progress of your Pulsar function using third-party tools. You can have the log sent to a central location, and you can scan them for error conditions, etc. Currently, Pulsar functions support multiple programming languages, including Java, Python, and Go. And most importantly, they can leverage third-party libraries. For example, in our case, we're going to use third-party libraries to support the execution of machine learning models within these functions themselves. So while they can be simplistic, very simple single methods of code, you can incorporate whatever sort of third-party libraries you want to get these additional programming capabilities built into these microservices that you're going to build based on Pulsar functions. So why were Pulsar functions built? What problems do they solve? Right? They were designed to create a computing infrastructure for Pulsar that helps ease the complexity of stream processing. We found that people who want to do stream processing oftentimes felt that they had to stand up an additional complex data stream processing engine that's very complex and difficult to operate, such as Apache Storm or Apache Flink or maybe Spark, and then plug it into your streaming system like a Kafka or a Pulsar, and then use that. But a lot of times that's a lot of overhead just to do some simple transformations, some simple processing logics, or implement microservices, right? Instead, you want to take a more serverless computing approach, and you can maximize your productivity, right? Because anybody who knows how to write a single method in Java can immediately be productive with Pulsar functions and start doing some simplistic transformations right away without having to learn how to, write Flink jobs and understand all the details of that and stand up a Flink cluster just to test these things out. So typically you want to use functions, while they're a great solution, they're not a solution for everything. There's a right time to use them and a wrong time. And they're designed for lightweight stream processing, right? They excel at basic use cases, such as transformations, simple per message transformations that can do normalizations or cleanups. And as I mentioned before, you can do change sequences of transformations on data from a single topic. So again, you can have a Pulsar function come in as an input topic, perform some data processing, output it to another one, which has another Pulsar function listening on it, which does another simple transformation of the data, and so on and so forth until you end up with a finalized processed data. Or in the case of an event-driven microservices, you can use it to pass data back and forth. So I'm listening on an event topic for an order to come in. I do the processing and for the warehouse or order fulfillment, for example. When I've done it, I have a tracking number. I can send that back to a topic, and then the microservice that needs to display that information back to the customer can read it from that topic and then display that information back. So let's talk about how to develop Pulsar functions. At a high level, Pulsar provides an SDK for this, so that there's a concept of native functions, and we won't focus on that today. Instead, I'm going to focus on the SDK that comes with Apache Pulsar, and specifically the one related to Java in this particular case. Although it is provided for Java, Python, and Go, and it provides a more complex API than the native functions as well. So again, you can with a context object, which is provided as part of the input parameter, it allows you to fan out messages. So you can output, instead of one single output topic, as we saw on the previous slide, you can output to many. There's a concept of stateful functions, so you can retain state between invocations of a function. Again, you can consume from and produce to different topics, etc. So lots of different capabilities built in to the SDK, and that's what we're going to leverage today within this demonstration. Last but not least, when you package a function for deployment, it is intended to be entirely self-contained. Within Pulsar and the Pulsar function workers, which I mentioned earlier, they're deployed and they're running in your Kubernetes environment, but they have no libraries available to you. So if your Pulsar functions use third-party libraries such as machine learning, which we'll use here, you must bundle all those dependencies along with it and deploy it. Now for Java-based functions, this is going to be a nar file for this example, but for Python functions, there's different options, and then for Go-based functions as well, it needs to be pre-compiled and packaged entirely as a Go file. But again, for our application, we're going to do a nar file, which has some dependencies I'll point out during the demonstration, that you have to include certain build tools within your project in order to take advantage of this. And with that, I'm going to show a demonstration on how to implement sentiment analysis of sentence data to simulate things like tweets. So random sentences will be fed into our Pulsar function. We'll use a third-party library to take that sentence, pass it through this machine learning library to determine what is the overall sentiment of this particular tweet. Is it positive? Is it negative? Is it neutral? And this code is all available at my GitHub repo here, shown here below, and we'll walk through that next. So let's explore the code from the repository. There are two Maven modules within this repo, the first being one called Sentiment Analysis Function. This represents a Java-based microservice that will be using the machine learning model to perform a sentiment analysis on raw tweet data. As you can see here, it contains a Java class called Sentiment Analysis Function that implements the function interface defined in the org Apache Pulsar Functions API. It is a typed interface which specifies the input type value coming in from the source topic as string, and we will be returning a type of analyzed tweet, which is a user-defined class that will contain the tweet text itself along with the calculated sentiment for that tweet. The only method defined in this interface is the one called process, found here, and we mark it with the override annotation. To note is that we're going to return a type of analyzed tweet, which is what is specified as the output type in the function, and these must match. Similarly, the input type was specified as string, and the input parameter, the first one, is going to be that same type, allowing you to have strongly typed data coming in so you can manipulate it in the manner you see fit. We have added a single guard and initialize method to make sure that we initialize this natural language processing library just once in order to perform it rather than do this multiple times. We can see that this library is an open source library, third-party library, available here, and we include it in the module as a definition here. So we include it as a normal dependency like you would any other Java class, and it's freely available inside the Pulsar functions themselves, which is really, really powerful. Not a lot is going on inside this particular method, but we just want to demonstrate the capabilities, right? So a tweet comes in, the text comes in, and then we leverage this third-party library, this machine learning model, to perform sentiment analysis on it. It calculates a sentiment for us, and as I mentioned before, we return a value that contains the original tweet text along with the calculated sentiment. And this is really it. This is the core of it, but it gives you an idea of what actually can be done. Now, in addition to including the third-party libraries, in the base POM, you can see that we've defined a plugin, a build plugin here, which is the NAR plugin. This bundles everything together in a unified single deployable module, as I discussed in the previous section, makes it easy for deployment. The second module is called a tweet simulator, and this is going to publish data out for us. It is also based on the Pulsar IO and functions framework, but it implements a different interface here called Source, which is part of the org Apache Pulsar IO.core framework. It allows you to integrate with systems, publish data in and out. In this case, we're using it to simulate tweet data, primarily because the tweet API is now locked down, and after 1,000 tweets, you're sort of out of luck for an entire month. For testing, we want many more tweets than that. So I've wrote this little class instead to generate data into that particular topic to feed our sentiment analysis function. This tweet source here reads data from a local file. I just created some random text, some sentences that come in, some random data that'll be passed through, and then we'll perform analysis on that. So that's really it. That's where the code is, and this can easily be built. If you go to your terminal and you run maven clean package, it will generate the NAR files for both the tweet source and the sentiment analysis function, which we will use for deployment in a minute. I also want to note that as part of this particular project, we have a Pulsar function or Pulsar cluster rather, that you want to run locally and can be started with the start brokers command, which is what we will use down here. You'll notice that we're already in that particular bin folder, so I'll go ahead and start the brokers now. So we have a Pulsar cluster to test against locally. Makes it very useful. It's self-contained. And I want to note here that I have specifically used the version 2.93 of Pulsar, and I've used a little bit of a trick to map the volumes, these internal volumes, to where these NARs are being built to. You can see it to the target directory here. I'm mapping it to a file system on the Pulsar cluster, which is going to make it easier to deploy these using the command line tool in a second. So this is, I did it once for the source and again for the analysis function as well. Also note that you want to make sure that you enable the function worker. By default, it is disabled in the Pulsar standalone, so you can do that by adding this particular setting and making sure that you do not have the NFW switch. A lot of times that's there, and that means no function worker. That disables it, so make sure that that is turned off. Once you've done that, you should have a Pulsar cluster up and running. Let's verify. Let's look at this Docker logs pulsar-f, and we can see it started. It's up and running. Everything is great. We're gonna use this to monitor the progress of our system. So now let's pivot and start generating the source data. So as you can see here, I've already copied and pasted in the command to do it. There's a command line tool in the Pulsar admin called source, and it has lots of different methods, the first of which is create, and then you can specify the name of what you want to name that particular source, and then you specify the archive file or the artifact that contains the source data. In this case, it's the nar file that we generated, and specify a destination topic. Where do I want this data to publish to? So we'll go ahead and execute that and look at the log here, and we should see it coming in, so we can see that it got received. The tweet simulator came in, it's being unpacked. The metadata is coming out. It has some information on how it was deployed. It was a source. The nar file is deployed. So if you want to get down at the details, you can check these things, and if there's any issues, check your log. If we do a get on that source, we can verify that it was deployed as we wanted. We can see the configuration values here. Everything looks correct. We can also check the status, right? So let's check the status of our source just to make sure that we're generating some data. And it's been executed 17 times already. So we can come over here and we can consume from the tweets in. So this particular source is publishing, again, as we saw, to the tweets in topic. So let's consume. This is another command we can run in a separate window. Create a Pulsar client to consume. N0 means consume indefinitely. Give it a unique subscription name and the topic name, which is going to match to where we're publishing the data. And let's verify that the data is coming in. We're going to see some startup information here about the kind of connection, but then shortly we'll start seeing the tweets coming in one by one. Data coming from that raw text file one at a time. So the source is working. Now let's pivot and start creating the Pulsar sentiment analysis function. So I have left in the code itself a method that encapsulates all this if you don't want to type it from memory, like I don't. So we'll go ahead and use this to recreate it. I want to break this down a little bit though. So again, we're executing a command inside Pulsar itself, and inside Pulsar there's an admin tool and a function subcommand, and we tell it to create a new Pulsar function. We specify with a -jar that where the entire artifact is to deploy, which is the sentiment analysis nar file we just created. The class name of the sentiment analysis function itself. So again, it's the full package name. This is the class we want it to run. The input parameters are going to be this tweets input topic here that data is coming into. And for our output, we're going to publish it to a different topic, default tweets out. And last but not least, if you want to, you can specify a log topic as well for informational data there, but that's really all we need. This should work correctly. If everything goes correctly, you'll see a command created successfully. Again, you'll see things in the log file coming in, letting you know that it was successfully received, how it was configured, the tenant namespace and name, class, everything else should match what you want. You can quickly verify this as well. Everything's up and running. If you have any sort of errors, it would be first noted here. If you want to also check on the status and get the configuration details at any point in the future, we can copy this real quick. Run the command here, and it should spit back out the configuration details that we sent in. Again, verifying it was deployed as we see fit. And if you want to update these, if you want to change the output topic, change the parallelism, things like that, you can change the behavior later. But it looks like everything is up and running. So now let's go and see what the output looks like. So again, as we saw earlier, it's writing as an output to tweets out, public default tweets out. So we're going to consume from that same topic over here in a separate consumer, and see this again. This is still the tweets coming in. So let's see how our machine learning model is working. Is it getting the information? Is it processing it correctly? We'll start up here shortly. Again, you see some connection details coming in, and sure enough, you're starting to see here was the original tweet, and it was assigned a sentiment of neutral. The next one comes in. Everyone was curious, positive, etc. So it starts coming in and matches. We can get in the most recent data, and we're doing some analysis on it. So it's event driven in that regard. As soon as something comes in, an analysis is done on it, and it's published out. And so you can see that this is moving, and it's going to work in tandem for a while, and that's not a problem. If you want to check the performance and how long the processing of each one of these tweets takes, you can use the stats command, which is going to give you some average processing latency. This is the average, obviously, processing time of each tweet. It's going to tell you how many tweets have been processed, how many over the lifetime of the tweet itself, and things like that. So lots of information is available. As you can see here, everything is working just fine as expected. So to summarize, we learned that event-driven microservices need a message bus to communicate between themselves, and Apache Pulsar is the perfect solution for this message bus. It provides the pub-sub semantics required by an event-driven architecture, while at the same time being horizontally scalable and supporting millions of topics. Pulsar also includes a native lightweight compute engine known as Pulsar Functions that allow you to easily build microservices with a few lines of code that follow the event-driven pattern. And last but not least, we showed you how you can easily incorporate third-party machine learning libraries into your functions to enhance these microservices with machine learning capabilities. I want to thank you for attending my talk, and let's keep in touch. You can scan the query code to get my contact details, follow me on Twitter, reach out to me on LinkedIn, and go get my code from GitHub. Again, thank you very much. Have a great day.